All right, so the last thing we're doing today is the laws of logarithms. We did look through one law, or rule, I guess, if you will. And we're going to look at just a couple more and how to simplify or what they're used for. So first off, the laws of logarithmic functions are directly related to the laws of exponents, since logarithmics are exponents. And what it means by that is, as I was showing earlier today, is that if you have an exponential equation, y equals a to the power of x, well, the logarithmic function of that is the inverse of an exponential function. And again, the inverse, I know we haven't talked about it very much at all this year, but is just when we flip the x and the y's. And so the log function is x equals a to the power of y. And so when we switch the x's and the y's, well, one of them ends up being an exponent. And just like the rules of exponents, the rules of logarithms are going to be very, very similar. And what I mean by that is in that when you have a log rule or an exponent rule such as x to the power of a times x to the power of b, we keep the base the same and we just add the exponents. All right, that's a rule from grade 9 and grade 10 and hopefully in grade 11. Again, I'm not sure what you have done so far this year, but logarithmic functions or logarithmic rules are going to work in a similar way. And so here's our laws or rules. The first one we did this morning, where again the log, this time there's just a little base a in there though, but it's going to be equal to if we just brought the exponent down in front. Then we have rule number 2 and rule number 3, which talk about the adding of logs. And you can see that if they have to have the same base, that's key here. But if we have log of x plus log of y, well, we can simplify that into log of x times y. And of course, they have to have the same base of a. In a similar way is that we have log x minus log y. That is equal to the log of x divided by y. Now, the one thing you got to watch out for here is the first log is what's going to be in the numerator, and the second log is going to be in the denominator. So that's something to watch out for. All right, so well, I'll do a couple here. An example number 1. Write each logarithm in the form r log a base a x. And so again, this is what we worked on this morning to solve exponential equations, but just going to go through a couple. Again, this is log with a base 4, 16 to the power of 3. And again, what we looked at today was bringing the 3 down in front. We have our log function. This one has a base of 4. Again, if you don't see a number there, it's a base of 10. And we have our 16 there. B, we can do the same thing. Again, there's our exponent of 2. So I can bring that down and multiply our log function. And this time we have a base of 5 and to the 625. All right, so again, that's the function we looked at earlier today. Now, the 2 other log rules I want to focus on here that we didn't do is that we have, and this should be in brackets here, write each expression as a sum or a difference of logarithms. Now, to make this more correct, I should put brackets around that. But how I could just rewrite that is if that I have 25 times 16 inside the log function. I'm just going to rewrite it using log rule number 2 here, where it would equal the log of 25, and because it's multiplying, plus the log of 16. And of course, I can't forget that this is based on a base of 5. There we go. So that's just one way to separate them. C, where we're looking at division. Again, the numerator's on the top, so that's got to be your first one here. So that would be, I could rewrite it as the log. It's a little big there for that, but the log of 10 divided by Oh man, I don't have one of those on here, so I have to write that in. Divided by the log of 3. So let's write those in. So divided by, and of course the base has to be 8 on both of them. So it's just another, again, using the log rules is another way to simplify, not in this situation, or express our logs in a different way, or to split them up. Going the other way. Now this is, here we're just in example 2, like I said, we just wrote the log in long form or split it up. Example 3, I want to work the other way where I am simplifying. All right, and so in this case, when I have the log of 81 plus the log of 9, and both have a base of 3, that plus sign means that I can write it as a log, single log, but yet with multiplying. And so I'd have the log, again, with a base 3. But in the brackets, I would have 81 times 9. And of course, I could do 81 times 9 if I got my calculator here, which I do. All right. And so I could rewrite it as, again, a single log, simplified log of base 3 of 729. And there we go. B. This time we got minus. And so that is going to refer to division. And so I could rewrite this log again as a single log, where I have log of base 4. But again, the first term is our numerator. So I got 128. All right, all over 64. Again, then I guess I could divide those two. 128 divided by 64 is actually just a 2. So I could say that log of base 4 with just a 2 here. So again, that's just simplifying our log. Now in C, it gets a little more complicated. So I got to follow Bedmas like normal here. And so I'm going to figure out what's in our square brackets first. So I've got my log of 2, 64, base 2, I should say, 64. Subtract. Now, in square brackets here, I'm going to write my log function as a single, or all that expression inside the square brackets as a single log. Again, it's subtraction, so I'm going to write log with base 2. Again, the first number here, 16, is our numerator, and the denominator is going to be 4. All right, so again, continually simplifying here, I have the log with base 2, 64 minus, I can simplify 16 divided by 4 is 4, so I have the log base 2 of 4. All right, so again, because they have the same base, I can even simplify this even further. Again, it's subtraction, so I've got the log base 2, and then I got 64 has got to be the numerator. That denominator is 4. And I could further simplify that because I can divide 64 by 4 nicely. So I got the log of base 2, and 64 divided by 4, 16. And actually, I could evaluate that. It doesn't say that. Write each success. I already wrote it as a single logarithm. But I could actually evaluate that, because what's that saying is there's your base is 2. We don't know what the exponent is, but the answer is 16. And in this case, I could evaluate that whole mess, because 2 to the power of 4 is equal to 16. There we go. It didn't ask us to do that, but I could do it. Probably have that in a future question here. Oh, I do. All right. Example 4, evaluate the following logarithmic expressions. So I'm going to actually figure stuff out. Now, you can see I got a combination here of pluses and minus, but again, they all have a base of 5. So I can do it all at once. And here's how I would do that. I would write the log of base 5. Now in brackets here, I got my 125 times 5, because those two logs are being added, but then subtract the log base 5, 25. So it means I'd have to divide by 25. All right, and if I do that, let me see here, I'm going to have the log of base 5. Let's see here, 125 times 5 divided by 25 is actually 25. Now it says evaluate, which I can switch this into exponential form, because again, there's my base. There's my, I don't know what the exponent is. That's what we're evaluating, and the answer is 25. Well, in this case, x is going to be equal to 2. So our final answer here is 2. All that. All right, let me see here. Let's try another one. C. All right, so we got the log base 2, 64 minus, all right, log base 2, 32 plus log base 2, 4. So again, I can write this out first as a single logarithm, where we have the log of base 2. All right, so first off, I'm going to have, let's see here, 64 divided by 32. All right, but then I got the plus 4, so I can actually multiply by the 4 on the numerator. Right there. All right, and now to simplify that, so I take 64 times 4. Okay, get 256. Divided by 32, I end up with 8. All right, so again, to solve this expression, I've got my base of 2. I don't know what the exponent is, but I do know the answer is 8. And 2 to the power of 3 would give you 8. So our answer here is 3. All right, so let's see what else we got here. Something a little different. Write each expression as a single logarithm. All right. All right, so we've got 2 log 20. Oh, okay, we got a bunch going on here. Plus 1/3 log 125 minus log of 20. You'll notice there's no little number here, so this means it's a base 10. It's assumed, and that's what's on your calculator. So I could rewrite this to get rid of using our log rules going the other way that we did this morning. And what I mean by that is, instead of writing 2 log 20, I'm going to write log of 20, but I'm going to put the exponent, move it back up on the 20. Plus, I'm going to do the same thing for the second part of this, where I'm going to write log of 125. Again, put the exponent on there of 1/3. And then I don't have to worry about the third one, so it's just going to be minus log of 20. Okay, so simplifying this now, we have the log of 20 squared. Okay, the log of 20 squared, well, that's the log. 20 squared is 20 times 20, which is 400. Plus, here's one, 125 to the 1/3. Now, this is, again, something that I covered in grade 11. I don't know what you did, but 125 to the 1/3 means you take the root, I said, 125, and there's a little 3 here. It means you're taking the third root of 125, which means you're looking for the number that multiplied by itself 3 times will give you 125. So not the square root, but the third root. And that number that works is actually 5, because 5 times 5 is 25, then times another 25 is 125. There we go, log of 5. And then, of course, minus log of 20. All right, so again, we're writing this as a single logarithm. Well, that means I'd have, let's see here, I better write this out. We've got the equals the log of 400 times 5, because we got that plus sign there, and then minus, so the 20 is going to be division. And then finally, I could write it as a single logarithm. I take 400 times 5 divided by 20. As a single logarithm, this would be log of 100, because that's what 400 times 5 divided by 20 is. Okay, let's try B. Okay, so again, I'm going to do the same method here. We have a half in front of this log, a quarter in front of this log, and nothing in front of this one. They all have a base of 4, though. All right, so we have the log. Again, I'm just going to reverse base 4 here. 64 is in the log, and then the 1/2 is going to come up, and that's going to be our exponent, plus the log of base 4, 16, and again, putting the exponent back on, which is 1/4, minus the log of base 4 with 16 there. No exponent to be moved. All right. Now, again, this is something I just covered right here, but I'm going to do it again. Because, again, I don't know what you did in grade 11. But I got 64 to the 1/2. That looks like this. You put a 64 there. You're finding the root, that number right here in the denominator, 2, the second root. That's another way of saying the square root. The second root is the square root. All right, so the square root of 64 is 8. There we go. Plus, but now I'm on to the next one here, where we have the log of base 4, but 16 to the 1/4. Well, 16 to the 1/4 means put a 16, a root sign, but the denominator here is a 4. So now I'm looking for the 4th root of 16, which means what number multiplied by itself 4 times will give you 16? And the answer is 2. 2 times 2 times 2 times 2 will give you 16. All right, minus, again, the log of 4 to the power of 16. All right, so I've simplified it using our log rules. Here we go, the last part. Let's see here. We have the log of base 4. Let's see here. 8 plus sign, so times 2 divided by 16, because it's a minus sign there. And, well, 8 times 2 is 16. Divided by 16 is just going to be a 1. So we're going to, as a single log, we're going to have the log, base 4, and then a 1 there. And that is as a simple log, or single log. All right, so now we got another one here. Woo! Example 6, use properties of logs to express that expression right there in terms of log 6x, log 6y, and log base 6z. Okay, so here we go. And this, again, is going to tie into some grade 11 exponential. Again, I'm not sure what you did. So we got the log base 6 here with the square root of that big expression. Now, I can rewrite this as the log. Now I'm going to start off by, whoops, we got the base 6 in there. I'm going to slide that 6 in there. I got x cubed, y squared, and a z on the bottom. Now the square root, as I mentioned up here with this 64 to the 1/2, to the power of 1/2 means take the square root. So instead of writing the square root sign, I'm going to put an exponent there of 1/2. All right, now I'm going to use my log rule here where I'm going to bring that exponent down in front. So I've got 1/2 times the log of base 6. And then I got x cubed, y squared, divided by z. All right, so now inside that log function, I guess I should put it in brackets. I have some multiplying and some division going on. So now I'm going to split it up using our log rules even more. I'm going to have 1/2 times this whole big thing. So I'm going to break it up. So I'm going to have big square brackets here. So the first part now is I'm going to write it as log base 6 x cubed plus, because I'm multiplying that y squared term, log, it's like undoing it, log base 6 y squared. Then I've got this divided by z, so minus sign, log base 6 z. There we go. Now, we're not quite there yet because what's it say here? We got x needs it in that form. All right. So on all of those, I'm going to bring the exponent down in front. So I got 1/2, again, multiplied by, again, I'm going to take this exponent 3 off the x using our log rule. So I'm going to have 3 times log base 6 x. Going to say do the same thing with the y here. So I got plus, bring the 2 down in front using my log rule, 2 times the log of base 6 y. And then the z, well, there's an exponent of 1 there, so that's not going to matter. So minus log base 6 z. All right, pretty much there. All you got to do now is the rainbow rule, or the distributive property, just times each term by 1/2. And so I end up with, let's see here, equals 1/2 times 3. That would be 3/2 log base 6 x. All right, then that's the first term. And then 1/2 times 2. Well, half of 2 is 1. So I'm just going to have plus log base 6 times in y there. And then 1/2 times minus the log. So that would be minus 1/2 log base 6 z. And there we go. I've just expressed this huge function here, this huge expression in terms of log base 6 x, log base 6 y, and log base 6 z. Woo! Using all my different log rules there, undoing and then redoing back up. All right.